Bayware enables NetOps to move at the speed and agility of DevOps. In this demo, I will show how programmable network microservices accelerate secure application deployment across hybrid and multi-clouds. Bayware gives each application its own secure network, all in software. I will show you how to deploy applications in hybrid and multi-cloud environments using Bayware's technology. First, I will show a new application which is full mesh connectivity in a test environment. I'll then show how to move this application to a policy-compliant production environment. The application we are using for this demo, called Getaway App, has several microservices, and the connectivity between these microservices is described in a high-level abstraction called a service graph. I will show how we will segment the application in the private cloud using the Bayware fabric, and how we will achieve a flow-level micro-segmentation in our private data center. After that, I'll move several microservices of this application to Amazon Cloud and show how encrypted site-to-cloud VPN will automatically be created. I will then move a couple of microservices to Google Cloud and Azure, where encrypted multi-cloud peering will automatically be established. Finally, I'll show how to make a small change in a programmable microservice to enforce policy for particular flows of this application to implement security and operational requirements. Here is the Getaway app. From the list, I can choose some cities around the world and based on their location, receive related weather, places, and news information. To make the demo clearer, I can see the workload identifier that provides this data. Now, I see that I have some workloads in my private cloud that provide data to my Getaway app. There are 6 application components: the HTTP proxy that receives requests from the internet, the Getaway app itself, a database, and 3 data sources: News Gateway, Places Gateway, and Weather Gateway. Here, you can see my target service graph for the microservices that comprise this application. At step 0, I have all the application components deployed in the IP fabric for testing purposes. In this IP fabric, I don't have any micro-segmentation, so the HTTP proxy can talk to any service, not only with the web application, but also, for example, with the Places Gateway. Of course, in my production environment, I won't want to have this full mesh connectivity. So to segment the application and to move into my production environment, I will deploy Bayware Fabric at step 1. After deploying the Bayware Fabric, I will show that application flows will be micro-segmented automatically, so the HTTP proxy will have access just to the Getaway app as described in the service graph. It will have no access to the Places Gateway or any other components. At step 2, I will move 4 application microservices into AWS Cloud, the web application itself, and 3 data providers. And I will show that we will preserve connectivity and security policy when we move components from the private data center to the public cloud. In the next step, I will move 2 microservices into Azure and GCP, and again preserve the same service graph, connectivity, and security policy. I will come back to step 4 later, where we can use Bayware to steer flows. Let's start then with step 0. I have my demo application, and I can check that it works in my private cloud in a flat network for testing purposes. Before I start with Bayware, I block the flat IP network. Now the application cannot work in my full mesh IP fabric. Let's start with Bayware. Step 1. I will deploy the Bayware fabric in my private cloud. As you can see, my enterprise environment has no Bayware components. I've just started the installation of the first Bayware processor on one of the virtual machines in my private data center, that is, my private cloud. As part of Bayware's processor, I installed a data path that is a software component to hold the forwarding tables and pass data packets. In this situation, I'm using Open vSwitch as the data path. After installation, the Bayware processor registers itself on the Bayware orchestrator, and now I have the first processor. This is the first node in my Bayware fabric. I will start 3 other Bayware processors so that in total I should have 4 processors in my private data centers for this demo. They are automatically registering themselves on the Bayware orchestrator and negotiating connectivity between themselves. We are using a secure neighbor discovery protocol to establish connectivity in the Bayware fabric. Now that I have a processor fabric, I can start deploying Bayware agents on the application workloads that I want to attach to this Bayware fabric. Again, I do everything with zero-touch configuration. As agents are registering, I can see a workload with the Getaway app, a workload with the Places Gateway, a workload with the HTTP proxy, my Weather Gateway workload, a database workload, and now I have a News Gateway workload. They will all be attached to the fabric. To connect its workloads, an agent starts negotiating connectivity with the nearest processor. This attaches this workload to the Bayware fabric. Even here in the private data center, we are using IPsec, so all connectivity between workloads and processors is secure. This is zero-touch workload attachment with automatic link encryption. Now I see that all 6 workloads have been registered and attached to the Bayware fabric. Let's check. Even though I blocked the IP fabric earlier, if the new Bayware fabric has re-enabled the application to work as designed with the micro-segmentation in place. It's a zero-trust network. No packets could cross the Bayware fabric until I enabled workload-specific connectivity and policy. I have the same connectivity that we have described in our service graph. I'm receiving from the same workloads data, but this data is received using the Bayware fabric. Instead of full mesh connectivity, now I see that the HTTP proxy can talk only to the web application front-end app as desired, and it cannot talk to any other components in this network. Also, only the application server can talk to the services that are the Weather API, Places API, and News API. It's perfect micro-segmentation. Note that I use crypto-based workload identities. I never use an IP address to define policy or connectivity for any particular application microservices. To move some of the application services to the public cloud, I use instances of AWS Virtual Private Clouds. I have previously established 2 standard VPCs in Amazon Cloud. Now, I will deploy at least one Bayware processor in each VPC. When I deploy them, I will use the same procedure I showed for the private cloud. Each processor in AWS registers itself to the Bayware orchestrator, and it automatically creates secure IPsec links between processors. Once processors are attached and registered, they extend the Bayware fabric. I can then move my application workloads to public clouds. To move workloads, I need to install a copy of the workload instance on the VPC and then start Bayware agents associated with each workload. As I start these agents, they register themselves and associate with the nearest Bayware processor. I see that now in AWS. I have my News Gateway, my Places Gateway, my Weather Gateway, and last, I have the web application itself. At this point, I don't need these same 4 workloads in my private cloud any longer, so I block them remotely. Now I can go to my Demo Getaway application to see the change in a source to AWS. Pay attention to what the data providers give for each source as I request the data. Now I receive weather data from a new workload in AWS, the same for Places and the same for News. When I go to my demo application and check the HTTP access to the microservices, I see that I have the same service graph that I had before. So the HTTP proxy can talk only to the front-end application and nothing else. At this point, I will move a couple of microservices into Google Cloud and Azure Cloud. I have established just one standard VPC in each cloud. I start one processor in Google Cloud and one processor in Azure Cloud. They will register themselves to my enterprise Bayware orchestrator. Now I see that I have a processor in Google Cloud and one in Azure Cloud. They negotiate connectivity with the Bayware fabric and will establish secure links with other processors. At this point, I can put instances of workloads and start workload agents in GCP and Azure. They will attach workloads to my Bayware fabric. In Azure, I have started the Places Gateway. In Google Cloud, I've started the Weather Gateway. Agents find the nearest processor. As you see, a workload in Google Cloud has found a processor in Google Cloud, and Azure finds the nearest processor that's processing in the Azure Cloud. Since I will no longer need the Places and Weather workloads in my AWS Cloud, I stop these 2 agents. They are no longer active in my AWS Cloud. I can go back to my application, and looking at the workload identifiers, I will request data for San Francisco to refresh the data. Now, I receive weather data from the workload in Google Cloud, Places data from the workload in Azure Cloud, and I'm still receiving news from the workload in AWS Cloud. I can check the HTTP access to the application microservices again and see that I have the same micro-segmentation. The HTTP proxy can talk only to the front-end application and cannot talk to any other components in my network. I built a multi-cloud mesh network with all links encrypted. Network services are entirely abstracted from the underlay providers, so when I moved workloads across private and public clouds, I didn't care about cloud-specific policy or connectivity implementations. Now back to step 4. All my network microservices are described in contracts. Since these are programmable, I have near real-time policy update and enforcement when I need it to redirect my flow. With the default configuration, the HTTP proxy sends a flow to the Getaway app using 2 transit nodes. Now let's imagine we need for some security and operational reasons to direct this flow through a particular node in our network. Let's say we will have some deep packet inspection services co-located at this node 3, and we want the flow from the HTTP proxy to the Getaway app to traverse this node. I'll show how we can do this with Bayware Fabric by updating a programmable network microservice. First, let me show you that BWKv3 is receiving no flows. In the Bayware orchestrator, I can look at the network microservice contract for this particular flow. In path params in my contract, I have not specified any particular node that should be traversed by this flow. Now, I set the BWKv3 as a transit node for this particular segment. Let's look at BWKv3. I see that now I have flow records that describe policy for this flow. I refresh the web application page. Now I can see that I use this particular node to send packets through from the HTTP proxy to my web application. To summarize, I showed how connectivity and policy can be programmable via network microservices. We used a workload-specific contract construct to do this. We saw zero-touch workload attachment with automatic link encryption that allowed us to build site-to-cloud VPN, and after that, to build a multi-cloud mesh network with all links encrypted. During this demo, I used a crypto-based workload identity. I never used an IP address to define policy or connectivity for any particular application microservices. We had fully role-based network policy descriptions with contracts and role in contracts. It's a zero-trust network. No packets could cross the Bayware fabric until I have described connectivity and policy. I showed that network services are entirely abstracted from the underlay providers so that when I moved workloads across private and public clouds, I didn't care about cloud-specific policy or connectivity implementations. All my network services are described in contracts. And I had a near real-time policy update and enforcement when I needed to redirect my flow.